Alright, now that we can solve a system of linear inequalities, we want to put this all together and answer sort of a bigger question, and that is we want to be able to solve a linear programming problem. The way a linear programming problem works is you're trying to optimize some function. So optimize means you're trying to find the maximum or the minimum value of. So say you want to maximize your profit, okay, that might be something we're interested in, but there are some constraints that you have to operate within. So for example, with profit, your cost of materials must be within the budget. You can only work your workers for so many hours, a day or a week, and you might have to consider cost of labor as well, so paying your workers. So anything that sort of limits your production, that would be called a constraint. And so the constraints are going to form a system of inequalities. So we know how to find the feasible region for a system of inequalities. So we can find the corner points of them. And then once we have our feasible region, we can check where within that feasible region does our optimization function get optimized. Where does the objective function, get optimized? So if we stick with this example of profit, we can find the feasible region based on our constraints, such as labor and materials cost. And then based off of that feasible region, we could see where the profit is maximized. And so we can figure out how much of our different things we should be producing. The key thing that's going to help us out here is this fundamental theorem of linear programming. So if there is an optimal value, so if there is a max or a min, then it's going to occur at one of the corner points. So if we can find the feasible region, which we should be able to do because we know how to solve a system of linear inequalities, so find the feasible region, then those corner points are going to have to be one or more of those corner points would be our solution, if we have a solution. So let's take a look at this example so we can see sort of how this all comes together. So we have a company that makes two styles of hair dryers, the Petite and the Deluxe. It takes 1 hour of labor to make the Petite hair dryer and 2 hours of labor to make the Deluxe. Materials are $4 and $3 respectively, and the profit is $5 and $6 respectively. The company can support, let's go ahead and highlight this, we can support 3,950 hours of labor, and we have $9,575 to spend on materials each week. So I can already see, knowing the hours, right, we had 1 hour of labor or 2 hours of labor, that's going to be related to our total labor hours, and the cost, $4 for the Petite, $3 for the Deluxe, that's going to have to relate to our materials budget. And now here the big question is, how many of each dryer should be made to maximize the profit? So just like we've done in the past, we're going to have to come up with a system of inequalities that describes this situation. Let's go ahead and figure out what our variables should be. Sometimes the hardest part of the question is figuring out what the variables are. And there's always a clue for what you should make the variables be, and that's in the question itself. So how many of each dryer? So that tells me that I would like to be able to answer how many Petite hair dryers and how many Deluxe hair dryers. So my variables should represent the different types of dryers. So I'm going to go ahead and let x1 be the number of Petite hair dryers, and we will let x2 be the number of Deluxe hair dryers. Okay, so when I've solved this system, x1 should be giving me Petite, x2 should be giving me Deluxe, and so I'll be able to answer the question here. Let's also go ahead and figure out our objective function, and that's determined also by the question. We are trying to maximize profit. And so this tells us that we should come up with a profit function, and we are trying to find the maximum of that function. So let's go ahead and let P represent profit. Okay, so our objective function I'll use fxn for function. Our objective function, P for profit, is going to be the profit that we get for each petite hairdryer plus the profit that we get for each deluxe hairdryer. Now the profit was given to us in the problem. I'll go ahead and do it in blue. Let's see, we said the profit was $5 for the petite and $6 for the deluxe. And so I get $5 for every petite hairdryer sold, plus the $6 that we get in profit for every deluxe hairdryer sold. So we would like to maximize this objective function subject to the constraints that are determined by the labor hours and the budget. So now let's go ahead and come up with those constraints. So let's see, let's do the labor hours first. We know that every petite hairdryer contributes 1 hour of labor. So you can say 1x1, or we can just leave it as x1. So x1 plus the 2 hours of labor that it takes for a deluxe hairdryer. So this is representing our total hours of labor in 1 week. This total hours of labor must be no more than 3,950 labor hours in 1 week. So we have a constraint here. We've restricted the total amount of labor hours that we can work. Let's see, our other constraint was the budget, right? The materials budget. And so let's see, it costs $4 for every petite hairdryer and $3 for every deluxe hairdryer. And so our total budget for materials must be no more than $9,575 per week. So these are our constraints. We have 2 more constraints that we need to add as well. And those are what we call the non-negative constraints. So the number of hair dryers has to be bigger than or equal to 0. So x1 has to be bigger than 0, x2 has to be bigger than 0. They could equal 0, but we just can't have a negative, okay? So the way we would want to write our problem, if it's going to be in the form of a standard linear programming problem, we would say that we want to maximize P subject to these constraints that we've been given right here. Okay? And so the way that we're going to do that is, let's find the feasible region from the constraints, and then we'll find the corner points and go from there. So let's see our feasible region first off. Let's see, we'll go ahead and just scooch, maybe not, we'll go ahead and just do it right here. I'm going to go ahead and graph the feasible region. I'm not going to go through finding all the points because we've done plenty of examples like that at this point. Let's see, we should have one line that comes down kind of like this and one that's less steep, sort of like this. Now finding the corner points, that is a little bit trickier. This diagonal line, this first diagonal line is the 4x1 plus 3x2 equals 9575, and then this shallower line is the x1 plus 2x2 equals 3950. So that's where I'm getting the 2 different lines. When I graphed the lines, I was able to get the x and y intercepts for them. So let's see, this is at 1975, and the x-intercept down here is at 2393.75. And let's see, we are going to need this corner because our feasible region turns out to be this bounded region close to the origin right there. So our feasible region came out in here. Again, I'm not going through all the steps to get the feasible region because we've already done several examples like that. So you follow the same steps that we did before. So we should have 4 corner points, and 3 of them we should know just from graphing it alone. So the x and y intercepts of all the lines we should know when we graph it. And so the one that we're going to have to do some algebra for is this corner point that's where the 2 lines cross each other, okay? So there's a couple ways that you could do that. We want to solve the system 4x1 plus 3x2 equals 9575. At the same time, x1 plus 2x2 is going to equal 3950. So use the techniques that we've done before. I would go ahead and use elimination or substitution. So x1 would equal 3950 minus 2x2. We'll go ahead and plug that into the first one right here and solve from there. Let's see, that should give us x2 equals 1245, and then if we take x2 and plug it into our equation for x1 comes out to 1460. So this corner point is the point 1460, let's see, 1460, comma 1245. That would be our corner point on the sort of the intersection point there. So now that we have all four of our corner points, we want to make what's called a corner point table or a corner point chart, and we just want to test each of the corner points in our objective function. So I'm going to go ahead and list the corner points. So here's my corner point. It's an x1, y1, or sorry, x1, x2 pair. And we're going to test it in the objective function, the profit function, 5x1 plus 6x2. So we didn't graph the objective function, right? We're only graphing the constraints, and then the corners of the constraints will be evaluated in the objective function. So let's go ahead and start with the first corner at the origin, 0, 0. Then our profit would be 5 times 0 plus 6 times 0, so profit would be 0. And that makes sense, right? If you produce nothing, then you should have no profit, okay? Let's try the next one. Let's sort of go clockwise around here. So I'm going to try the corner that's at 0, 1975. Our profit would be 5 times 0 plus 6 times 1975. And this should come out to 11,850. So notice that this profit is higher than the profit at 0, 0, which makes sense. If we're producing more things, right, then if we're producing more than nothing, then we should be making more profit. Notice that at this corner point, we produced no petite hair dryers, right? We only produced the deluxe hair dryers. So let's see if we do a mixture. So our corner point C that we found, let's see, 1460 and 1245. So our profit, if we plug in x1 and x2, this should come out to 14,770, which is higher than what we had previously. Okay, interesting. So let's see what if we go to the fourth and final corner point, where we produce no deluxe hair dryers and only petite hair dryers. So this would be 2393.75, comma 0. Our profit in this case comes out to $11,968.75. And so the maximum profit occurred at the corner point that was at 1460 and 1245. So we want to go ahead and answer the question that was asked in the original problem. And that question was, how many of each dryer should be made to maximize the profit? So we should make 1,460 petite, and we should make 1,245 deluxe. Now the question didn't ask it, but it's a likely question where I could ask you, how many of each thing should you make, and what is the maximum profit? And so let's also note that the maximum profit was $14,770. Okay? So, quick recap here. We find the feasible region, find the corner points of the feasible region, and test the corner points in the objective function. In this case, that was the profit function. Whichever one gives us the highest objective value, so the highest profit here, that is the point that we're interested in. And then you always want to make sure that you interpret your numbers, okay? So make sure you answer the question. The question was how many of each type, and so we want to make sure we say how many petite and how many deluxe.